All right, we are in Precalculus. Today's date is 2/26. 2/26. I'm using the smartboard today. No, it's not. It's not the 27th. You're not going to make me look. So sigma notation. Sigma notation is pretty cool. It's a way of condensing ways of asking questions, adding things. Before we begin too much, vocab, sequence. What do I mean when I'm talking about a sequence? What is a sequence? Not quite. Not quite. Give me an example of a sequence.
Like a pattern?
I mean, it depends how you state the pattern. Here, I'll give you a sequence. Ready? Orange, pear, banana. That's a sequence of fruit. Should I give you a sequence of the numbers? 1, 3, 5, 7, 9. Here's a sequence. Give me a number. 2. What's your rule?
Multiply by 2.
Well, that's a geometric sequence. So 2, 4, 8. Whoa, don't know what happened there. 2, 4, 8, 16, etc. That is a sequence. In order to turn that into a series, what needs to be the change?
The thing that causes it?
No, the sequence, the only difference is you change the comma to a plus. Yeah, so it's going to be 2 plus 4 plus 8 plus 16. That's a series. So we've only been dealing with sequences up until this point. Today is our first day where we're actually dealing with series. So let's talk about what I mean by partial sum. You'll hear partial sums for the rest of your math career. I don't know how long that's going to be if you decide to not do math. You might never hear about partial sums again. Partial sums are used quite a bit in calculus. It's just a way of saying, hey, look at those 3 things. It's the opposite of an infinite sum. If I had an infinite number, then that's an infinite sum. A partial sum is, well, you only look at a certain number of elements in that series. So a partial sum is just, another name for it, by the way, is a finite, write it down, finite series. Finite series, but a finite series. So it's basically just a fancy way of saying series. Everything that we're dealing with today is really partial sums because I'm only looking at a finite number of those added numbers. So let's talk about the notation. This guy, this giant symbol here, this symbol is called a sigma. Yeah, it's right up there. You're looking up at the Greek letters. And you will see this when you see sororities and fraternities at whatever college you end up going to. They will probably use sigma because it's a cool letter. I love it. It's the Greek letter for S. My last name starts with an S, so I use sigma a lot. It's pretty cool. But yeah, so sigma. Practice drawing it. Like practice drawing on the side. It has some teeth. It looks like that.
So that's like an equal sign. No, not equal sign. It's like 2 less than's and 1 greater than.
Yeah, I guess less than or greater than. I see it with teeth. A lot of people don't do the teeth. They just go choo, 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 and make it really lazy. But make it look nice.
That would seem like kind of confusing because it would look like a whole like fragment.
Yeah, I agree. You will eventually be drawing those today, so get used to how they work. So what does this mean? By the way, this guy's name is sigma, S-I-G-M-A, M-A, sig. Starting to hiccup today. That is called sigma. That giant letter is a capital sigma. Lowercase sigma looks like this. This is a lowercase sigma. Lower case sigma. And lowercase sigma is kind of like a T. It's kind of like a capital T with an attachment.
So like a J where you keep on going around.
Yeah, or a J where you keep on going. So J, and then comes around, yeah. So that's a sigma, and you can see a sigma up there. Lowercase sigma, where is it? There it is. We won't be using lowercase sigma. We'll be using capital sigmas. Sigma is an S. S stands for sum. Sum these things. In fact, that's where the basics of calculus come in. We use integrals, right? Which actually look like an S. Before they started using integrals, they used Riemann sums, which is a sum of those infinitely small slices underneath the curve. So this is just relating, it used to be sigma notation. That was the definition of what an integral actually is. Calculus reference. So coming here, we say that this is the index. We start with an index. It can be whatever letter you want. I just randomly chose n. It can be A, I, J, K, whatever you want. I chose n. And it says my index is going to start at 0. So this is the start. So n is going to start at 0. The value of n is going to end at this value. So I'm going to start at 0 and end once I get to the value of 3. So it's going to go 0, then 1, then 2, then 3. What does that look like? So let's plug it in. When I plug in 0, 2 times 0 plus 1 is just 1. So I'm going to actually write out 2 times 0 plus 1. That was the first piece.
Will the second piece be 2 times 1?
2 times 1 plus 1. Yeah, so again, it is a series, so these are separated by addition signs. The next one is now going to be 2 times 1. The index has gone up. The next, is it indices? Indices is plural. So it's gone. The index has gone up, still plus 1, same equation. And I'm going to go until this value, this index, is going to end at 3. So keep going until you hit 3. So then plus 2 times 2 plus 1. I guess I should, for the sake of staying consistent, I should use square brackets. And then finally, plus 2 times 3 plus 1. Oh, and of course I'm going to scroll down. Plus 1. So what numbers does this represent? 2 times 0 is 0, plus 1 is 1. So that's 1 plus 3 plus 5 plus 7. So far, so good? Notice that this 2n plus 1, this directly relates to an explicit formula for finding a sequence, not series, I was about to say series, a sequence. This 2n plus 1 is a sequence of 1, 3, 5, 7, on, and then our sigma notation told us, hey, take the values from 0 to 3, the 0th value being 1, first value, second value, third value, add up those 4 values. So let's do that. 3 plus 7.
Oh, wait, 3 plus 7, sorry, 10.
10 plus 5 plus 1. So this whole thing evaluates to 16. This sigma from n equals 0 to 3 of 2n plus 1 is 16. Let's try another one. Just play around with it. So k squared. I'm starting with an index where k is equal to 1. So what's my first value going to be?
It would be 1 squared.
1 squared. Then
Plus
2 squared.
3 squared. Plus 4 squared. Plus 5 squared.
Plus 3 squared. Plus, okay, why is this not working? Plus 4 squared plus 5 squared. There it goes. My finger is on the other side, so it communicates using radar from this direction. By my finger being over there, it shouldn't affect it. I think it's just my computer can't handle recording and talking to the smartboard all at the same time. And I also write a little bit fast. All right, 1 squared is?
1,
2 squared?
4, 9, 16, and 25. Which all equals, so that's 25 plus 25 equals 50. So it's 55.
55. There's our answer. Let's box it. Yeah, again, you can do this really quick because 16 and 4 is 20.
I did 16 plus 9 equals 25. 25 plus 25
That's-
equals 50.
That's a good way to do it too.
Plus 5 equals-
Yeah, let's try example 3. 3i. So what are my values going to be? It's going to be 3 times 0 first, right? So it's going to be 0 plus,
So it's 0 plus 3. Oh, we're already simplifying?
yeah, we're just going to start skipping steps now.
So it's 0 plus 3 plus 6 plus 9 or plus 12.
We know that's the last value because when I plug in 4, which is the n, when I plug in 4 times 3 is 12. That is indeed the last value. All right, and then add these up.
So 6 plus 3 equals 9. 9 plus 9 equals 18. 18 plus 12 equals 30.
30. All right. One more example.
Does the 3 in front of the sigma means you're going to multiply all of them?
Yeah, so at the very end, we're going to multiply by 3. Don't worry about the 3 until the very end. Let's just do I.
So it's 0 plus 1 plus 2 plus 3 plus 7.
And then all of that is going to be multiplied by 3. Okay, well, let's simplify the inside of the parentheses. 1 plus 2 plus 3 plus 4 is 10, right?
Yeah. So it's going to all equal 30.
30 again. What do you notice about example 3 and example 2?
It's the same thing. It's just that they distributed the 3 out.
Yeah, you factored out the 3. It's the reverse of distribution, right? Yeah, so you reverse distributed a 3. You factored out a 3, and you still get the same answer, which leads us to our rule. So property 1. This is a property that you will need to know about sigma notation. So if I have some c that I can factor out, c has been factored out. That means I can pull it outside of the sigma notation. So that c is being pulled out,
So
and
whatever c is, it gets pulled out.
whatever factor was. In this case, this is a number. C is just a number. This case up there is 3. So c is just a constant. It's a number. So that c is going to be pulled out. And now let's write the sigma notation. So sigma, this is where we actually get to practice writing sigma notation. The index is still the same. It's still k is equal to m. It still ends at m, or n, I should say. N is in, what do they use for the native phonetic alphabet? November. And then the c is gone, so I just am left with a sub k, which represents whatever is left. And there's your formula. This is your first property of the 2 properties that you need to know today. If you have a number that's being multiplied, just factor it outside, and it makes it a much easier problem. All right, and we're on to the back side.
Well, it depends. If it's just like with example 2, it's just 3i, it makes it quicker.
Yeah, the whole idea is eventually we'll get really complex things, and we need to be able to use the properties to simplify it.
If c was in like say like 2n plus 1, if 3 was in there, like multiplied by 3, then yeah, it'd be more better to just take it out.
Yeah, I agree. Let's try example 4. Go ahead and simplify. When I plug in 1, I get the value of 11. When I plug in 2, I get, when I plug in 3,
13,
when I plug in 4,
14.
what's going on? 14 plus 15. Why does that keep doing it? Plus 15. And do I end there, or do I keep going? That's it, yeah, because I plug in 5 as my last value. That's the very top. 5 plus 10 is 15. I need to add all of these together.
So 12 plus 13 equals 25. 25 plus 15 equals 40. 40 plus 25 equals 65.
Some really good mental math you have. 65. That was a little bit challenging. Would you agree that that was kind of hard? Okay, let's go to P. So if I just do P, plug in 1.
That would just be 1 plus 2 plus 3 plus 4 plus 5.
What does that equal to?
So 5 plus 5 equals 10 plus 5 equals
15. So that was a little bit easier than the last problem. Ooh, this is a tricky one. Example 6. There's no P. There's no P, so what do I do?
So it'd just be 10.
So when I plug in 1,
Oh, wait, 10 plus 10 plus 10 plus 10.
10 plus 10. So this was the value when P was 1. P is equal to 1. Then P was equal to 2 is this value. Plus 10, that was 3. Plus 10, that was 4. Plus 10, that was 5. What's 10 plus 10 plus 10 plus 10 plus 10? Or 5 times 10?
20. I'm just kidding.
So funny. What do you notice between example 4, 5, and 6?
So 4 is adding 10. Like 5 is just P. 6 is just 10.
Yeah, it's like 5 and 6 were separating example 4 into 2 different problems.
Oh, 50 plus 50 plus 15 equals 65.
Oh, look at that. Yeah. So if I'm looking at 15 and 50, which were the answers for example 5 and 6, if I add those two together, the answer for example 4, which makes sense because we separated the sigma notation. So our sigma notation said sigma, sigma, and then the 10 for example 6, and you just add them together. And that brings us to our final property that you need to know for today.
So does one mean just sigma of A equals to sigma of B?
It doesn't mean that they're equal, it just means that I can separate them into two different sigma problems. So how do I say that? I want to separate this into two sigma problems. So I have sigma, why letting me draw down there? Whoa, that's so trippy. If I go like that, okay. Weird, man. I've never had that error before. All right, so sigma from k equals m to n of a sub k. So that's the first problem, and I can add that to the second problem, right? I can add that to also a sigma from k equals m to n of the second problem, which was b sub k. There's your second property that you need to know, which means you can just separate it into two different problems whenever you see addition. The key thing here is these were adding or subtracting. This can be add or subtract. So when you're adding or subtracting, turn it into two different problems. You can also factor out something. Those are our two rules. Those need to be in your notes. Cool, you good? Our homework is super, super easy. You don't even need to use these properties, but you should practice them. Tonight's homework is all about playing with these properties, making sure you really understand them. And that concludes the notes.